We use an IP address to identify a device in an internet. An IP address has 32 bits in length. Some of those bits identify the subnet, or more generally the network that a device is attached to, and the remaining bits identify that individual device in the network. We'll try and explain that today so you can work out how IP addresses are structured. I know you're all excited about submitting your assignment and you're waiting for your results on your assignment, but that will be another week or two, so don't worry too much. Worry about the quiz, worry about the final exam. We're going to talk today, how do we structure the IP address? 32 bits, which parts represent the network, which parts represent the host? We finished last week with saying that for humans to look at IP addresses, this is a 32-bit IP address. What we do is we convert it into the dotted decimal form, where we divide it into portions of 8 bits, so 4 groups of 8 bits, convert each 8-bit binary number into a decimal value between 0 and 255, and combine them with dots to get the same IP address, but just a different way to write it down on a piece of paper or to represent it. We'll see some more examples of how we do that conversion, but basically you take the first 8 bits, convert to decimal, the next 8 bits, convert to decimal, you get 4 decimal numbers, and we write them down separated by dots. Of those 32 bits, some of those bits represent the network that a device is attached to, and some represent the host. We'll talk about the structure, but let's first talk about why that's useful. Here's our example internet. We have 3 different subnets or networks. And in this simple case, we have 4 hosts, but there may be more hosts. And some routers. So similar to an example internet we covered in the previous topic, in the previous lectures. We said in the previous lectures when we route via the networks. That is, if host 1 wants to send something to host 3, the way the routing works is that the IP datagram is sent to the router attached to network B, and then a router attached to network C, and then this router delivers to host 4, our destination. That is, in the routing tables of those routers, and also in the hosts, we don't store the individual host addresses, we store network addresses. That is, we'd store, to reach subnet C, host 1 would send to router 1. To reach subnet B, host 1 would send to router 1. So we talk about reaching subnets or networks, not individual hosts. For that to work, we need part of the address to identify the subnet and also part to identify the hosts. So each 32-bit IP address can be split into 2 parts. The network portion, which identifies the subnet, and the host portion, which identifies the device. For example, we could say that this device is C3. This is C4, A1, and A2. Where the addresses now, we've used the network address, A and C, combined with a device address, 1, 2, and 3, 4. Our IP addresses are not letters and decimal numbers. Our IP addresses are 32 bits. But the same concept. Some of those bits represent the subnet. The remaining bits represent the host. So let's go through some examples to illustrate that. Here's an example IP address, and let's say it's the IP address of host 1, device 1. 32 bits, I've just separated into blocks of 8 bits, so I put some spacing in there just so we can see it, but it's just a 32-bit value. We need to know where do we split this address, which bits represent the network of this device, and which bits represent the individual device. We said that host 1 conceptually has the address A1. A represents the network, 1 represents the device. Every device on that same network would be A something, A1, A2, A3, A4, and so on. Some of these bits in the IP address represent the subnet, A in our example, and some represent the host, 1 in our example. There are different schemes to determine where this split is between the network portion and the host portion. The scheme that we use today is called classless addressing, and we have an additional identifier called an address mask or a subnet mask. We use a subnet mask or an address mask to tell us which of these 32 bits identify our subnet or our network and which represent our host. As an example, let's say in this case the first 10 bits represent the network. As a result, the remaining 22 bits represent the host. So we need some scheme to tell us where do we split the address into the two different identifiers. The rules that we have with addresses in our internet are every host or every device attached to a subnet must have the same network portion in their IP address. That is, every device attached to subnet A must be A followed by something else. A1, A2, A3, A4. In an IP address, in this example, every device attached to this subnet must start with these first 10 bits. If this is the IP address of host A1, if it's defined to be this, then host A2 must start with this. That is, the first 10 bits must be the same, because it's on the same network. If two devices are on the same network, they must have the same network portion in their IP address. The host portion must be different from other devices on that same network. That is, for host A2, the last 22 bits must be different from any other device that's on that same subnet. I'll give a different one. this 32-bit value or this last 22 bits is different from here. It's just this last 2 bits differ. So that's just an example where we have two hosts, A1 and A2. They're attached physically to the same subnet. In our example, we've called it subnet A. Therefore, their IP addresses in the host portion, the first 10 bits, must be the same. The first 10 bits here are the same as the first 10 bits here. Because they're on the same subnet, they must have the same first 10 bits in this example. The last 22 bits must be different between those two hosts. That is, to get different addresses for each device, the last 22 bits must be different. If I had a third host on this same subnet, it would have the same first 10 bits and a different last 22 bits. And so on. We could have multiple different hosts on that one subnet A. Let's consider hosts C3 and C4. And the addresses I'm using here I've just made up for the example. So I'll explain a little bit more about why I chose, or the selection of, why the first 10 bits here. That was just chosen for my example. It doesn't have to be the first 10 bits. In this subnet, I said that the first 10 bits represent the network portion of the address. In subnet C, let's say it's the first 20 bits. Which means of our 32-bit address, the first 20 bits identify the subnet C. This is in 8, 16 here. Following the same rules as we had with host A1 and host A2, host C4 must have the same first 20 bits. C3 and C4 are on the same subnet. Their network portion must be identical. And in this case, the first 20 bits must be identical. And two hosts on the same subnet, their host portion of the address must be different. They must be unique. Because they're different hosts, they need different addresses. Which value? In fact, we have how many? We've got 12 bits here for the host portion. It just has to be different from the other hosts. In this case, we just have one other host. There are many different combinations possible here. I'm just choosing a simple one. Will I? Let's not choose. The last 12 bits for host C3 are different than the last 12 bits for host C4, because the last 12 bits identify the host inside that subnet, and they must be unique portions of the address. I just chose an example there which differs in these bits. So an IP address of a device has two parts. A set of bits that identify the network that that device is attached to, and a set of bits which identify that device on that network. And the rules are, in our internet, all different networks or subnets must have different network portions. This network portion, the first 20 bits, must be different from over here, because A and C are different subnets in the same internet. If we gave an example for subnet B, it must be different from A and C. That is the network portion. That's the first rule. All subnets have a different network portion in their IP address. Within one subnet, all hosts must have a different host portion, so we can uniquely identify those hosts. So hosts C3 and C4 have a different last 12 bits. Hosts A1 and A2 have a different last, how many do we have? 22 bits. Where do we divide? In these two different examples, I said in this case it was the first 10 bits. In this case, it's the first 20 bits that identify the network portion. It's in fact, it can be any value. So it's up to the designer of the network and the internet to select the most appropriate location to split between the network and host portion. What's the difference? It has an impact on the number of hosts allowed within a subnet. Let's look at this case. Subnet A. First 10 bits represent the network. The last 22 bits represent the host within that network. With 22 bits, so 10 bits for the network, 22 bits for the host portion. With 22 bits for the host portion, that means there are 2 to the power of 22 possible different values. With 22 bits, we've got 2 to the power of 22 different values. In theory, we could have a maximum of 2 to the power of 22 different hosts on that subnet. If we have 20 bits for our network, remember our IP address is always 32 bits. If we have 20 bits for the network portion, we have 12 bits remaining for the host portion, meaning we have a maximum of 2 to the power of 12 possible hosts on that subnet C. What's 2 to the power of 12? About 4,000 possible devices can be attached to this subnet C. Okay, now we're building the subnet for SIT. We need to choose a range of addresses, that is, choose the number of bits that we have to be allocated to hosts, such that we can give addresses to all of our computers in our subnet. How many computers in SIT? Well, hundreds of computers. Probably not 4,000. If you count all the laptops, all the office PCs, all the labs and so on, hundreds of computers, we'd say. So with SIT, because we have 100s of computers and we need to give all of those computers unique addresses, they're all on the same subnet, say subnet C, then this split would be okay, because we have 12 bits to allocate to individual computers, giving us a possible maximum number of devices attached of 4,096. What if we did something different and split and split 26 bits for the network portion, 6 bits remaining for the host portion? Leaves us 2 to the power of 6. 2 to the power of 6 is how many values? 64. If we use this way to split up the network portion and host portion, we'd have 6 bits available to allocate to the host portion, giving us 2 to the power of 6 possible values, 64 possible values, which means on our subnet we could have a maximum of 64 computers attached. Because all computers attached need to have unique host portions, so we cannot have more than 64. That would not be enough for SIT because we have more than 64 computers. So the more bits we allocate for the network portion, the less we have for the host portion, and therefore the less hosts, in theory, or in maximum, we can attach to that subnet. So depending upon the organisation's requirements, the split between network and host portion can be decided, depending on how many hosts they want to attach. SIT needs more than 64, but probably less than 4096. Maybe we have 500 computers, so maybe 10 bits for the host portion would be enough, in case we can expand in the future. The other aspect is every subnet needs a unique network portion. The less bits we have for the network portion, the less subnets we can have. With 26 bits allocated to the network portion, there's 2 to the power of 26 possible values. In theory, if we just use this split, then we could have 2 to the power of 26 different subnets in the world. If the split was 1022, we'd have 2 to the power of 10 possible subnets in the world. 2 to the power of 10 is 1,000, about 1,000. We have many more than 1,000 different subnets in the internet today. In the world, we have hundreds of thousands of organisations that want to have their own subnet. So we need to trade off between having sufficient bits to be able to represent the set of subnets we want in the internet in the world, and the set of bits that we need to allow subnets that have enough hosts for what each organisation needs. There's no one perfect split. If I build my own internet, my own subnet at home, and I just have 10 computers, then I only need, and I'm going to have no more than 20 computers, then I only need maybe 5 bits for the host portion. Allow me 32 devices attached. If I used 12 bits for the host portion and I only had 20 computers, of those 20, or of the 4,096 IP addresses allocated to my subnet, I'd only use 20 of them. And those other 3,900 or so, or almost 4,000, would be wasted, would not be used. And we start to get problems of that we run out of IP addresses. That is, there are many IP addresses that are just not allocated to devices. So if some organisation has a lot but doesn't use them, and another organisation has a lot of computers, then they would like to use some of their IP addresses, some of the free ones, because we only have a limited number of IP addresses. So the design of the scheme should be such that it supports many different subnets of different sizes. The more bits in the host portion means the larger the size the subnet can be. In practice today, how do you know where the split is between 10 and 22 bits, or between 20 and 12, or any other value that splits those 32? This split is assigned by the organisations that assign you IP addresses. If you start your own company, then maybe you would go to an ISP, an internet service provider, and they would assign you a block of addresses with some subnet portion, and depending upon what your requirements were, that is how many addresses you need, they may decide to give you a host portion with 8 bits, 12 bits, or whatever they have available based on your requirements. So it's managed by the organisations that assign addresses. There's a slide later that talks about that, and that's managed within a country, which is managed within a region, and there's managed globally as the assignment of IP addresses. An important thing that we haven't mentioned is, how do we know that the split is at 10 bits? I told you in this example it's at 10 bits. There's a way to represent that in an IP address. The way that we do it is called a subnet mask. And what we do is we have an additional IP address, a second IP address, that tells us which bits represent the network portion and which bits represent the host portion. So here's an IP address, 32-bit value. Here's a corresponding subnet mask. Where we have a 1 in the subnet mask, it means the corresponding bit in the IP address represents the network portion. And where we have a 0, the corresponding bit represents the host portion. So in this case, how many do we have? The first 22 bits of our IP address are in the network portion. The remaining 10 bits in our IP address represent the host portion. That's what this special subnet mask tells us. Wherever there's a 1 here, that means the bit here is in the network portion. So I could write the subnet mask for these addresses. Because we said the first 10 bits were the network portion, therefore the subnet mask, the first 10 bits would be 1 and the remaining would be zeros. So in fact nowadays we have both an IP address and another address, the subnet mask or the address mask. The mask simply tells us where this split is. Similar, we'd have a mask here which the first 20 bits would be 1, the last 12 bits would be 0, to say that the split between the network and the host portion is after the 20th bit. So in fact we have two values, the address, the IP address of the device, and its corresponding mask. We know that we can convert these to dotted decimal values. What's the dotted decimal IP address of host A1? Try and work it out. Use your calculator if possible, if you have one.
This router has a limitation on the number of hosts that it can handle.
Does a router have a limitation on the number of hosts? In theory, no. In practice, it may have a memory limitation. That is, you only have so much RAM to store values in. In theory, there's nothing to stop you from adding more RAM. In practice, it may slow down. If you add more RAM, you need to search through more values. You can convert these addresses to dotted decimal notation. I'm not going to do it in my head. I'll get it wrong. we just take each 8 bits, convert to a decimal number. The first 8 bits, we have 24. No, that's a different one. 16. This is 192. This is 0. And this is 1. The IP address of host A1 is this sequence of 32 bits, or in the simpler form, 16.192.0.1. And host A2, you can check, would be 16.192.0.2. It's only the last 2 bits that differ between those 2 hosts. And we can do the same for the subnet mask. Instead of having to write the subnet mask as 32 bits, we can convert it to a dotted decimal form. 8 ones is 255. What have we got? 192. 0, 0. So remember, you need to be able to convert a 32-bit binary IP address into the dotted decimal notation. Take 8 bits at a time, convert to decimal, you get 255. Next 8 bits, 192, 0, 0. This is the subnet mask. This is host A2, this is host A1. The 2 hosts are on the same subnet and have the same subnet mask. This is a 9, 192. There's even a simpler form for writing the address mask. So in this example, we now have an IP address and a subnet mask. Both can be written in the binary form or the dotted decimal form. The address mask can also be written in a shortened slash form where you count the number of bits, 10, number of bits that are 1, and slash 10. This subnet mask has 10 bits of 1. That is, the network portion is 10 bits. We could write it as slash 10. In our hosts C3 and C4, we could do the conversion. We need to convert this to decimal. It's 96.1. Is it 96? Yep. .65. This is 65, and this is 1. The subnet mask in this example, we said it's the first 20 bits. So we could write 20 ones followed by 12 zeros as the subnet mask. Or in a simpler version, we could convert that to dotted decimal. Or in an even simpler version, we just write slash, then the number of ones, 20 bits. So this represents 2 addresses, or 2 identifiers. The address of the device and its subnet mask. This slash 20 notation tells us that the subnet mask, the first 20 bits are 1, or the first 20 bits are the network portion. In this example, we had an IP address of host A1, the corresponding subnet mask in the binary value, in the dotted decimal form, and in the slash shortened form. 10 bits in the network portion. Of course, the computing devices use the binary form, but we may often see them in the dotted decimal form or in a subnet mask as the slash notation. So you need to know how to convert between them. You'll learn how to convert between them by practicing. We may have some more practice in some examples towards the end. Any questions about the concept so far? So a device, yep, okay. How can we know how many networks or how many hosts? First, let's say that the subnet mask for a particular subnet is given to us by an organization. That is, if I want to create my own network, subnet C, I need to go to an organization and get a range of IP addresses. And they would give me a subnet mask. And they'll say, okay, you have this network portion, these 10 bits, which means you have a subnet mask which is /10. How do we know? So the question is, how do we know the number of networks and hosts? Is to do with the number of bits that we have to allocate. Number of hosts is the easiest. In this example, we had 20 bits allocated for the network, 12 bits for the host portion. With 12 bits, we can only have 2 to the power of 12 possible values. With a binary 12-bit number, there's only 2 to the power of 12 possible values, from all zeros increasing up to all ones. So there'll be some exceptions later, but the maximum number of hosts that we could have on this subnet is 2 to the power of 12, 4096. So the length of the host portion tells us the maximum number of hosts we can have on that subnet. So the maximum we can have on subnet C is 2 to the power of 12. On subnet A is 2 to the power of 22 with these examples. Similar concept can be applied for the number of networks, because we have a certain number of bits allocated for the network portion. Every network in the internet must have a unique network portion. A, B, and C must have different network portions. Therefore, depending upon the number of bits we have to allocate there, it limits the number of networks in the internet. That becomes more complex because they can have different length network portions. So it's not easy to calculate the exact number of networks we can have in the internet nowadays. But we can calculate, given a subnet mask, what's the maximum number of hosts you can have in that subnet. Any other questions before we look at some of the special cases? Yep.
The address of the host can we determine the number of bits in network?
So, in fact, every device needs 2 addresses now. The IP address of that device and the subnet mask. You can think they go together. I'll show you an example on my computer. On my computer, I have my internet address. In this example, 10.10.99.251, and I have the mask here. Sorry, it's wrapped around 255.255.248.0. So now every device or every interface needs those 2 values: the address, the IP address, and the corresponding subnet mask. And the subnet mask tells us where is this split in the IP address. Which bits represent the network, which bits represent the host portion of the network, of the address. And that may be different on different subnets. This is allocated for my interface when I connect to the wireless LAN. Maybe when I connect to the wired Ethernet, I may attach to a different subnet, and it may have a different subnet mask. So that may be different on different subnets. That is, A, B, and C may have different masks. We've spoke about hosts, that is A1, A2, C3, C4. The same applies for routers. Routers also have IP addresses. We think of IP addresses assigned to interfaces. This host has one interface, say a wired interface. This router also has an interface. So there'll be an IP address here, maybe it's A3. That is, the IP address of this router from this interface would start with the same 10 bits, followed by a unique value for the last 22 bits. Same as hosts, routers have IP addresses. Same addressing scheme. Except the router normally has 2 or more IP addresses because a router is attached to 2 different subnets. Router R1 is attached to subnet A, so it would have an address starting with this 10 bits, and it's also attached to subnet B, so it would have another address depending upon the subnet mask and the network address for subnet B. And router R2 would have 2 addresses. Same as my laptop has an address when it connects to the wireless LAN, which is one subnet. If this was my laptop here, and I connected to the wired network, then maybe I'm connecting to a different subnet, and I'd get a different IP address. I cannot show that because I'm not connected to the wired LAN. Think every interface of a device attached to a subnet has an IP address. That IP address also has a corresponding subnet mask. The subnet mask tells us, or tells the device, which bits in the IP address represent the network and which bits represent that host within the network. All hosts on the same subnet have the same network portion of the address. All hosts on the same subnet have a unique host portion of the address. All subnets in an internet have a unique network portion. And we use that information in our routing and delivering IP datagrams through the internet. If we remember back to our routing tables last week, router R1 stored an entry that says to reach network C, send to R2. It doesn't store the value C in the routing table, it stores an address that represents network C. What address represents network C? What address represents network C? Have a look up here. The first 20 bits represent this subnet. So the network portion of the IP address represents a subnet. So in fact, there's a special case address for every subnet. This was the address for host C3 and C4. This was the same address but in the dotted decimal notation and a network mask of /20. An address for subnet C is the first 20 bits. So this is one of our first special case addresses. They're listed on a subsequent slide. A network address represents an entire subnet, an entire network. The first 20 bits, the network portion, the remaining bits are all 0. Where the blue line represents the split between the network portion and the host portion. We call this a subnet address, or most commonly a network address. It's not a mask, it's an address of a particular network. So rather than saying network C, I would say network 0110. This would be the address of that subnet, where the host portion is set to this special case of all zeros. And we can convert that to dotted decimal. Same subnet mask. That's 64. 96, 1, 64, 0. So in fact we could be more precise here. It may not be very large to read, but we could say that this is subnet 96, 1, 64, 0/20. Instead of writing subnet C, I give it an address. This is device C3. We have 96, 1, 65, 1/20. That was our address C3. And C4, 96, 1, 72, 1. So our two hosts have an IP address and a corresponding subnet mask. The binary values are here. This is the dotted decimal value for C3. The dotted decimal value for C4 would be 96, 1. This, remember we just group in 8 bits. This value is what, 64 plus 8, which is 72. And this is 1. So C4, 96, 1, 72.1/20. They have the same subnet mask, /20. And the address of this entire subnet is 96.164.0/20. Other hosts, if they existed, must have the same first 20 bits. The remaining 12 bits must be different from these two hosts. So we've introduced our first special case address. We use addresses to represent subnets, where the bits of the network portion are for that subnet. The bits of the host portion are all zeros. That's the special case. A host cannot use this special address. My computer cannot have an IP address where the host portion bits are all 0. That's not allowed. If I try to configure my computer like that, probably the operating system will tell me that's not available, it's an error. And especially if someone tries to send something to me, it will not be delivered to me. We could do the same for B and A. The network address for A, 0001000011 followed by all zeros. What did I say, 192? This subnet is 16.192.0.0/10. A1 is this address, 16.192.0.1/10, where /10 is the subnet mask, meaning the first 10 bits of the network portion. Host A2 is 16.192.0.2/10. The subnet mask is /10, or in dotted decimal notation 255.192.0.0. We could do similar for B if we had an example. So a network address is a special case address. We cannot use it to assign to devices on our internet. There are other special case addresses. So the network address, it identifies a subnet in the internet. All bits in the host portion are 0. That's the rule. If I want to send an IP datagram from A1 to C3, then the destination address is that of C3, which is 96.165.1. That's the destination. Sometimes I would like to send an IP datagram from A1 to everyone on this subnet. That process is called broadcast. One source sends to multiple or everyone on a particular network is called broadcast. And there are two types of broadcast. There's what's called directed broadcast, where one host on any subnet sends an IP datagram and they want it to be delivered on all hosts on another subnet or on a specific subnet. So if A1 wants to send to everyone on this subnet, it would use directed broadcast. It would do a broadcast directed to a specific subnet. The way that works in terms of IP addresses, when we send an IP datagram, we don't set the IP address of a host, we use the special directed broadcast address. And every subnet has a directed broadcast address. All bits in the network portion are that for the subnet, all bits in the host portion are 1. Let's show an example. We're running out of space. Directed BC, directed broadcast here. For this subnet, the directed broadcast address, the first 10 bits are the same. Same for host A1, A2, same for the subnet address, the network address. But the last 22 bits are 1. That is the directed broadcast address for this subnet. Similar to the network address. In a network address, the host bits are 0. In a directed broadcast address, the host bits are 1. The network portion is the same. If we convert this to dotted decimal, we would get, running out of space, but if we convert this to dotted decimal, the directed broadcast in red, it'll be 16.255.255.255. If we have 8 ones, we get 255. So that is the address that we use if someone wants to send an IP datagram to everyone on this subnet. They would set this as the destination address. For subnet example here, the director broadcasts, the same network portion, the remaining bits are 1. And we convert it 96, 1, what do we get? 79. (96.1.79.255). Network address is a special case address. All host bits are 0. Director broadcast address is a special case where all host bits are 1. The conversions between the binary and the dotted decimal values, I've gone through quickly. I have the answers from before, but you can do that with a calculator or however you want to calculate the conversion. But you need to know the process. Take the 32 bits, split into 8-bit chunks, get 4 decimal values. That's all. In all of these cases, there's nothing different when I do the conversion between broadcast, network, subnet mask, IP addresses. We always use the same way to convert between binary to dotted decimal. So if our host A1 wanted to send a datagram to everyone on subnet 96.164.0, they would create an IP datagram and set the destination address to be 96.179.255. If everything's configured correctly, that one datagram would go to the first router, then it will be sent to router R2, and then router 2 would send it to all of those hosts. So everyone receives a copy. That's broadcast directed to one subnet. There's another type of broadcast, local broadcast. Directed is if you want to send to a specific subnet on the internet. Local broadcast is if you want to send to your own subnet, the one that you're locally attached to. If I want to send a message to every other computer on SIT subnet, I could use local broadcast because my computer is on SIT subnet. If I want to send broadcast to everyone on the Facebook subnet, and I know the IP address of their subnet somewhere in the US, I would use directed broadcast. I would send it to their subnet and then broadcast within there. But if I want to broadcast to everyone on my own subnet, I can use local broadcast. So there's a difference. Directed broadcast, because of security issues, is usually not supported. In theory, it's possible. In practice, not many people will allow that to work. That is, I cannot send a message to everyone on Facebook's network or everyone on any other company's network. Security would restrict that. Local broadcast, there's another special address. All bits, all 32 bits are 1. 255, 255, 255, 255. So in any subnet, the local broadcast address is the same. This host wants to send to all of these other hosts, set the destination to be 255, 255, 255, 255, or all ones in binary, 32 ones. And it should be delivered to every host on this subnet. So that's a special address, all ones address, the local broadcast address. There's another special address where there's all bits are 0, 32 zeros, 0.0.0.0 in dotted decimal. That's only used if, in very special cases, when your host starts, you turn on your computer, you don't have an address and you need to discover an address. You could send a datagram and set that address, all zeros, as the source. We're not going to explain how it's used. Maybe later in next semester you'll see that it's used especially, say, in DHCP, which some of you would have heard of and used. But just know that the address with 32 zeros is a special case address called the startup source address. And finally, there's a special address if you want to send to yourself. Just for testing, if my computer wants to send an IP datagram to itself, not out onto the network, but just within the computer, within the operating system, there's what's called a loopback address. Loopback is that as if you have a cable coming out of your computer going into your computer. This address identifies the current host itself, and the structure is that the first 8 bits are this sequence. 0 followed by 7 ones, followed by anything. 0 followed by 7 ones followed by anything is a loopback address. The common one that you've seen, 0 followed by 7 ones is 127 in decimal, followed by anything. And often the anything may be this, but it could be because those 3 addresses all start with the same special sequence of 0 followed by 7 ones, they are all considered a loopback address. In theory, if you send a datagram to any of those 3 addresses, you will receive that datagram. You just send it to yourself. The most common one you'll see is the 127001. Most computers have a loopback interface configured just for special cases. For example, testing whether you can send and receive datagrams. Here it is on my computer, 127001. So, a device in the internet needs an IP address to communicate. That device on a particular subnet must have a unique host address, host portion of the address. All devices on the one subnet must have a unique host portion. All the devices on one subnet must have the same network portion. The split between the network and host portion is determined by the subnet mask, where the subnet mask is a 32-bit value, where the bit 1s indicate the network portion, bit 0s indicate the host portion. We can write an IP address in the dotted decimal notation. Both an IP address, a subnet mask, a directed broadcast, any of these 32-bit values we can write in a dotted decimal notation. Also, there's a very short form for subnet masks. If the first 10 bits are 1, we can simply write /10 instead of having to write the dotted decimal notation or the binary version. All subnets have a special network address where the host portion of the address is all zeros. That's the blue one here. No, it's not. It's the... We don't have a written example, I don't think. Here's an example of a network address. The network portion is the same. The host portion is all zeros. Oh, we do have an example. This one. Every subnet has a network address. Every subnet has a directed broadcast address where the host portion is all ones. So remember, network address, host portion all zeros. Directed broadcast, host portion all ones. There's a special case local broadcast address, 32 bits are 1. That is, all bits are 1. And there's a special case source address, all bits are 0. We don't commonly see that. And there's special case loopback addresses. First 8 bits, 0 followed by 7 ones. This 127 style address. And that's the main structure of IP addresses in the internet. When you configure the IP address of your computer, you must follow those rules. If you don't, then maybe you will not be able to communicate. Something will most likely go wrong eventually. And there's nothing to stop you from misconfiguring the address. I can set the address on my computer to be anything. There's nothing to stop me from doing that. Except if I set it to something that doesn't follow these rules, then I may not be able to communicate. So it's normally up to the person who configures the devices to set the appropriate addresses. If you make mistakes, your network may not work. Some final points on where we get addresses from and some special cases that you may see. To make things more complex, there are some range of addresses that are used just internally for organisations. The ranges that are available for what's called private networks, there's 10, 000 up to 10, 255, 255, 255. Anything within this range is an address that you can give to a device inside an organisation, but it cannot be used to communicate with anyone outside that organisation. I want to build my own private network, no attachment to the outside world. I can use an address in these ranges. I can use any address, but the recommended values is address in these ranges. Another range is 172.16, and another one which you'll commonly see is this 192.168 range of addresses. These are commonly used if your network is behind a special device that hides you from the rest of the world, called a network address translator. When you connect to your ISP at home via your ADSL modem gets what's called a public IP address, and your computer attached to that modem gets a private IP address. No one outside in the world can see your private IP address. They only see the public IP address. So your ADSL modem must do some translation of the public to the private. That gets complex, and we're not going to cover how that works. I just mention these is because you may see these in practice. For this course, we'll assume every address that we see is public. In practice, it's not true. There are some private addresses. You've seen the addresses on my computer. You can see the address on your own computer using different software, using the graphical interface, using command line. You can find your IP address. You can find, normally listed is the IP address, the subnet mask, and the directed broadcast address. You should be able to find all three values. I think you can do this in your own time. I want to finish on one more slide first. Work out how to find the particular values. First, know how to convert between the binary value and the dotted decimal value. That's key. If you can't do that, you won't be able to do most of the other steps. Remember that a network address, we take the network portion and set the host portion to all zeros. Directed broadcast, take the network portion, set the host portion to all ones. And then you can find out, given some IP address and a subnet mask, you can find what's the corresponding network address, because you find the bits which represent the network portion and the host portion, and then you can find the network address and the directed broadcast address. Coming back to how many devices are attached to a particular subnet. We said if we have 6 bits for the host portion, we have 64 possible hosts, 64 possible devices. Except 2 of those addresses are reserved for special cases. With 6 bits, we have 64 possible values, ranging from 6 zeros up to 6 ones. But that special case of 6 zeros is used for the network address. And the special case of 6 ones is used for the directed broadcast address. So your device cannot use either of those 2 addresses. So the number of hosts that can be attached to a subnet which has a host portion of 6 bits is 62. 64 minus those 2 special cases. The number of devices that can be attached to a subnet which has, what do we have, 22 bits in the host portion. This has 10 bits in the network portion, 22 in the host portion, is 2 to the power of 22 minus 2, minus the 2 special cases, minus the network address, all zeros, and directed broadcast, all ones. So consider that. Class-full addressing, we're not going to focus on. We spoke about what's called classless addresses. The split between network and host portion is defined by the subnet mask. In the past, there were other ways to do that. Class-full was the original approach. We're not going to cover that. The last thing we want to say, where do you get an IP address from? There is a global organisation that assigns IP addresses to different organisations in the world. The Internet Assigned Numbers Authority manages the assignment of IP addresses. In fact, they delegate it to different organisations throughout the world. In the Asia-Pacific region, there's APNIC. This centre manages the assignment of IP addresses in Asia-Pacific, and that delegates to individual countries. So in Thailand, THNIC. And this is the organisation in Thailand that allocates IP addresses to organisations within the country. If you set up your own company and you want to attach that direct to the internet, you may need to go to them and say, okay, I'm going to set up a network and I want a maximum of 200 computers attached. Give me a range of IP addresses. Specifically, give me a network address. It must be unique in the world, and that's why it's managed by different organisations. They would choose a unique unused value and assign your organisation a network address, including the subnet mask. And then you would go back and build your network, and on every device you attach to that network, you would give it an IP address within the network range that was assigned to you. So it's up to you to manage inside your subnet. You get your network address from some organisation within the country, which comes from some global authority. That's a fast but hopefully sufficient coverage of the structure of IP addresses. So the way to make sure you understand this is to practice. In last year, there's a handout that has a number of practice questions. I'll point you to that via email, but you'll find it on the website from last year's course. It basically gives you a set of IP addresses and asks you questions about them. If you can answer all those questions correctly, you should know everything about IP addresses that you need. So I'll point to that tomorrow, but make sure you practice how to convert between dotted decimal and binary and understand the special cases and the structure of network addresses, subnet masks and host addresses.